number 19. In problem number 8, so that's this picture right here. So it's hard for me to show both at the same time, so let's just describe what we're looking at here. We've got a track, and it starts at height h. Okay, so it's going to come sliding down, and of course as it falls, the potential energy is changing to kinetic energy. It's speeding up, and then it's going to move into this circular track of radius r, and they're going to ask us questions about what's happening right here at this location. Okay? What are the magnitudes of the horizontal component and the vertical component of the net force acting on the block at 2? All right, so that was at that spot right there. What is the net force acting on it? The horizontal and vertical components of the net force. Okay, here we go. So the work done by gravity between those 2 points, right? Here the height is 5r, and here the height is r. So my delta H is 4r, 5r minus r. So that's what I'm using here. My delta H for the work done by gravity is 4 times the radius. So there we go. They told me the mass was 0.032 kilograms, or 32 grams. And so I multiply all that together. There's my work done by gravity. So I know all that work has converted potential energy to kinetic energy. So my kinetic energy then at that point is 0.15 joules. Set it equal to 1/2 mv squared and solve for v. And I see that the thing is moving at 3.07 meters per second. I needed to figure that out because they're asking me for the horizontal and vertical components of the forces acting on the mass. I know when it gets to that point, right, when it gets to that point, it's going to have weight. There's the weight. And it's going to have a centripetal force because it's moving in a circle. And what is providing that centripetal force? Well, the track, of course, provides the normal force. Okay? So that normal force is what is providing my centripetal force. So I know the centripetal force is mv squared over r. Now that I know it's going 3.07 meters per second, I can plug that in for my velocity. The radius of the circle we know is 12. The mass we know. So there's my normal force, 2.5 newtons. Okay, that is going to be my horizontal component of the net force acting on the weight. Then the weight of the mass is just mg, so 0.31. So I know this is the vertical force, this is the horizontal force. Now my net force is, when it's moving in that circle, right, here it is. There's my normal force. Here is my weight. So the net force acting on this mass is the vector sum, right, using the parallelogram rule. There is the net force. And when we talked about uniform circular motion, that's when something moves at constant speed. And when in uniform circular motion, if it's moving at constant speed, there is no tangential component of force. Now we have a tangential component of force, and the effect it's going to have is it's going to be slowing down. Sure, as this thing goes up the circle, it slows down the higher it goes up the circle. And that's what's causing that to happen. Okay? All right, let's look at part C now. At what height, h, should the block be released from rest so that it is on the verge of losing contact with the track at the top of the loop? When we get to the top of the circle, the normal force is what's providing the centripetal force. When that goes to 0, that's when it's just about to fall off the track. I would show you a video that I've seen before, but it's maybe not the best video. You've probably seen it. Some skateboarder decided he was going to do a loop-the-loop, you know, and he wasn't going fast enough, and he fell. His normal force became 0, and he did not have enough speed to keep him moving through the circle, and he fell. And the reason I wouldn't want to show it in class is because he landed on his head, and I think he injured himself severely. If you really want to see it, you can probably find it on the internet. Anyway, here we go. So when it just begins to lose contact, that's when the normal force is 0, and we're going to have some minimum velocity to keep it moving in a circle without falling out of the circle. So here's that minimum velocity where the weight is the centripetal force only, without the help of any normal force. And so that solves to square root of g times r. So I can plug in those numbers. So there's my minimum speed that I need to make it around the circle. I'm going to use my reference point as this highest point of the loop. That's my reference point for h equals 0. Why do I want to do that? Well, because then when I'm at that spot, at the highest point of the loop, then I have 0 potential energy. So I can say when I'm at the top, all of my energy is kinetic, 1/2 mv squared, right? And then when I solve for PE, that will be the height above the top of the loop that I need to be to get this much kinetic energy when I get to the height of the top of the loop. Okay, so I just figured out that V needed to be 1.08 at the top of the loop, so I'm going to plug that in here and solve for H, and so I get 0.06, and now keeping in mind where my reference point is, that's the height above the top of the loop. So the top of the loop is 0.24, so I add that height to it, and that is how high up the ramp compared to the ground now that the block needs to start from. Okay. So let's take a look at part D now. Graph the magnitude of the normal force on the block at the top of the loop versus initial height h for the range 0 to 6 times the radius. Okay. So we got to get an equation for, there it said, the normal force as a function of the height. So that's my goal here, to get an equation for normal force with my variable h as the only changing variable. Okay, so first of all, the centripetal force at the top is the normal force plus the weight. All right, and this is what I'm trying to get an equation for, the normal force. So I solve that for normal force. My centripetal force, of course, is mv squared over r. That simplifies to this right here. And then, if I look at my potential energy, the height, wherever that is, right, wherever my starting point is, that's where I'm 100% potential energy. It starts from rest. So my potential energy at the top equals the kinetic energy at the bottom, where delta H is the change from this position to this position. What matters is the difference in height between the starting spot and the ending spot. Okay? So all of that potential energy associated with that height change becomes kinetic energy. That's what I'm saying here. Okay? And the delta H, what is delta H? Well, that's height minus 2r, right? This up here is my height from the ground. There's H. And then delta H is here, right? And this height right here is twice the radius of the circle. Okay? So my delta H then is H minus 2r. Okay, as usual, m's cancel out. And now I see that here's my velocity as a function of my starting position. So I'm going to take that and sub it in right here for v squared. And the reason I'm doing that is because I need to get my normal force in terms of h, right? So far over here, my normal force is in terms of velocity. So I want to get my normal force in terms of h. So I'm going to make that substitution. And then after I make that substitution, I simplify it. And this is the equation that I get. The normal force, you see, G, M, and R, those are all fixed numbers. M and G, that's a fixed number. Here's my variable. So you recognize this equation as y equals mx plus b. This is my y-intercept. This is my slope. So I got my computer. There we go. And there's the equation that I came up with. So there's my slope. And when you plug in those numbers, you see that number comes out to be 5 this number right here. And then negative 5 GM. Of course, if you follow this down, that's where, way down here is a negative y-intercept. So this tells me right here, this is my minimum starting height, right, in order to get around the circle. Because this is where the normal force becomes 0. So if I go any lower than this, I won't make it over the loop. If I go higher than that, then the loop has to help me provide a normal force of this magnitude to keep me moving in that size circle.